Imagine waking in the dark and with a single touch, light floods the room. Or picture a city skyline where buildings pulse with color, each bulb responding to a command you never heard. That instantaneous control feels almost magical, but behind it lies a vast, carefully choreographed system, from distant power plants to the smart light in your hand. Today, we trace that invisible journey and reveal how electricity reaches your home and becomes the smart light that knows when to dim, brighten, or change color. Electricity begins its life at generation stations. These can be traditional coal and gas plants, nuclear reactors, or increasingly wind farms and solar arrays. Each source converts energy, chemical, nuclear, kinetic, or radiant, into electrical energy, usually in the form of alternating current. These generators produce electricity at relatively low voltages, which is efficient for creating power, but inefficient for long-distance travel. To solve this, the voltage is stepped up by transformers at the plant, sometimes to hundreds of thousands of volts. High voltages reduce energy loss as electricity races across transmission lines, spanning plains, rivers, and mountains to reach population centers. At the transmission level, a web of high-voltage lines carries electricity to regional substations. Here, large transformers step the voltage down to levels more suitable for distribution. Distribution networks branch out from these substations like capillaries from an artery. Poles, underground cables, and substations weave through neighborhoods, delivering electricity to businesses and homes. Along the way, grid operators constantly balance supply and demand. They monitor frequency and voltage, ensuring steadiness. Even small imbalances can ripple through the system, causing outages or equipment damage. Now focus on the moment electricity arrives at your street. A local distribution transformer, often mounted on a utility pole or in a green box, reduces the voltage to the familiar 120 or 240 volts used in homes. Wires run from this transformer to your breaker panel, the house's electrical nervous system. Circuit breakers and fuses protect circuits from overload, while wiring distributes power to outlets, appliances, and lights. That's the physical journey of electricity. But for smart lights, there's another layer: communication. Smart lights combine power and data. Some smart bulbs contain built-in wireless radios, Wi-Fi, Zigbee, Z-Wave, or Bluetooth, and a small processor. Others rely on smart switches or hubs that mediate commands between your phone and the bulb. When you tap an app or speak a command, a digital message travels over your home network or through a hub, telling the bulb to change state. The light's onboard processor interprets the command and modulates current to LEDs, altering brightness, color, temperature, or hue. The electrical energy still comes from the grid, but the intelligence controlling the energy is a layer of microelectronics and software. Efficiency plays a central role. LEDs use far less power than incandescent bulbs for the same light output, reducing both your bills and strain on the grid. Smart scheduling and occupancy sensors shift usage away from peak times, helping grid operators by smoothing demand curves. Vehicle-to-grid technologies and home batteries introduce even more flexibility. During peak generation, homes can absorb excess power. During peak demand, stored energy can be dispatched back to the grid. Security and resilience are equally important. Smart devices that control lights can be targets for hackers, so encryption and secure update pathways are necessary. Grid resilience involves redundancy, microgrids, and rapid fault detection to restore power after storms or failures. Distributed generation, rooftop solar, and neighborhood batteries can keep lights on locally even when larger grid segments fail. From turbine and solar panel to transmission line, transformer, breaker panel, and that smart bulb on your desk, electricity flows through layers of physics, engineering, and software. Each step must be balanced: voltage, safety, efficiency, and data. The next time you voice a command and the room responds, remember the invisible symphony behind it: a modern grid designed not just to deliver power, but to deliver intelligence.